Hello everyone, let's discuss the spring semester of the Fluid Dynamics module. First, let's discuss a one-dimensional flow. Consider a flow in a fluid that takes place purely in the x direction, and the fluid velocity is u, which is equal to u of t and x, I, where u is known. A particle path is determined by solving the initial value problem dx over dt is equal to u of t and x, with the initial condition x of naught equaling x naught, where x naught is given. Now, let's state existence and uniqueness. It is possible to prove that the solution to the differential equation with initial condition exists and is unique in interval t from 0 to a for some a if the velocity field satisfies the Lipschitz condition that the modulus of u of t and x minus u of t and y is less than or equal to m times the modulus of x minus y for all real x and y for t from 0 to a and constant m. Now, let's discuss how the Lipschitz relates to continuity. A function satisfying the Lipschitz condition is continuous, but the converse is not necessarily true. Then, let's talk about how the Lipschitz condition relates to differentiability. A function may be Lipschitz continuous on an interval, but not everywhere differentiable on that interval. Following on, let's discuss the exact compared to approximate solutions. The solution to the problem can be written as x is equal to x of t. The trouble is, in general, we cannot solve analytically to find x of t. Imagine, however, that we do know what x of t is. Then we could plot the path on a set of t versus x axes. We will call this the true path. Our goal is to construct a discrete approximation to the true path. To do this, we define a discrete set of points tk for k going from 0, 1, 2, etc. and obtain approximation xk at each tk point so that xk is approximately x of tk. That is, xk is approximately the correct solution at the point tk. Let us call the sequence of points xk, yk in the xy space the approximation path. Now, let's move on to discussing Eulers method. This is the simplest method of constructing the discrete approximation path tk xk. We apply the rule tk equals kh, xk plus 1 equals h of u of tk xk for k going from 0, 1, 2, etc. for the chosen value of h to the system. The constant h is called the step length. Applying this for each k value is called taking one Euler step. It is an explicit method as the new value xk plus 1 is determined explicitly at each time step in terms of known value. Next, let's discuss the derivation of Euler's method. First, we derive Euler's steps from a geometric viewpoint. We consider the tangent to the true path x of t at the initial point t equals 0. The slope of the tangent is dx over dt evaluated at t equals 0, which is equal to u of 0 x naught. The idea is to take the next point in the approximate path at the point t1 x1, where t1 is equal to 8. We have that the difference in x over h is equal to dx over dt evaluated at t equals 0, which is equal to u of 0 x naught, but the difference in x is equal to x1 minus x naught, so x1 is equal to x naught plus h u of 0 x naught, which equals x naught plus h u of t naught x naught, since t naught is equal to 0. We then repeat, taking the next slope at the point t equals h. In general, at the k plus 1th Euler step, we have that x of k plus 1 is equal to xk plus h of u of tk xk, where tk is equal to kh. Alternatively, we can apply Taylor's theorem to derive Euler's method. Recall that Taylor's theorem tells us that for a function f of x expanded about a point a, we have that f of x is equal to f of a plus f dash of a times x minus a plus all the way up to 1 over k factorial times the kth derivative of f evaluated at a times x minus a to the k plus rk, where the remainder rk of x is equal to 1 over k plus 1 factorial times the k plus 1th derivative of of f evaluated at psi times x minus a to the k plus 1 for some psi between a and x. Now we expand the solution path x of t about the point tk. Writing x of tk plus h is equal to x of tk plus h times x dash of tk plus h squared over 2 times x double dash of psi, which is equal to x of tk plus h of u of tk x of tk plus h squared over 2 x double dash of psi for some psi between tk and tk plus h. Note that we have truncated the Taylor series and expressing the remaining terms in the infinite series as the compact error term h squared over 2 x double dash of psi, which depends on a point psi somewhere in the given interval. If the error term is small and can be dropped, we have that x of tk plus h is equal to x of tk plus h of u of tk x of tk, which suggests the following rule for constructing an approximation set. X sub k plus 1 is equal to x sub k plus h times u of tk xk, where tk is equal to kh for k going from 0 to 1 to etc. Now let's move on to defining local and global errors. The error committed at one k step of a method is called the local error. The total error accrued over a sequence of individual k steps is called the global error. So after k steps, the global error is the modulus of x of tk minus xk. That is the difference between the current approximation and the exact solution. Next, let's discuss some analysis of the error for Eulers method. The error at the kth step of a method is ek, which is equal to the modulus of capital EK, where capital EK plus 1 is equal to x of tk plus 1 minus x sub k plus 1. Since tk plus 1 equals tk plus h, we use a Taylor expansion to write e of k plus 1 is equal to x of tk minus xk plus 1 plus h times x dash of tk plus h squared over 2 x double dash of psi k, where psi k is between tk and tk plus 1. Using the original differential equation, we have that ek plus 1 equals x of tk minus xk plus 1 plus h of u of tk x of tk plus h squared x double dash of psi a. One Euler step gives that xk plus 1 equals xk plus h of u of tk xk. So we have that ek plus 1 is equal to x of tk minus xk plus h times u of tk x of tk minus u of tk xk plus h squared over 2 x double dash of psi k. Thus, e of k plus 1 is equal to ek plus h times u of tk x of tk minus u of tk xk plus h squared over 2 x double dash of psi k. For the local error, we assume that the solution at the kth step is known exactly, so ek equals 0. Thus, ek plus 1 equals h times u of tk x of tk minus u of tk xk plus h squared over 2 x double dash of psi k. This is the local error at the kth step. For the global error, we sum the local error at every step. Thus, we consider the cumulative local error at the k plus 1 step to get h times the sum from j equals 0 k of u of tj x of tj minus u of tj xj plus h squared over 2 times the sum from j equals 0 to k of x double dash of psi j. This is the expression of the global error. If we assume that u is a function of t, then the global error at the step k plus 1 simplifies to h squared over 2 times the sum from j equals 0 to k of x double dash of psi j. This is of order kh squared, that is k lots of the local error of size h squared. Since tk equals kh, the global error at the point tk is of typical size htk. For a fixed step length h, the global error increases linearly with the independent variable. Alternatively, for a fixed value of tk, the error is proportional to h. Note that technically the cumulative local error is of order kh squared over 2 x double dash of psi, and so it depends on x double dash of psi. Next, let's discuss the general relationship between the local and the global error. In general, the global error might not be simply on the order of k lots of the local error of size h squared. The reason is that a local error commuted at one step may have an impact on what happens at a subsequent step. Next, let's move on to discuss the second order Runge-Kutta method. In the first step, we compute uk is equal to u of tk xk. The second step, we set xpred equals xk plus hu tk xk. For the third step, we compute upred is equal to u of tk plus h xpred. For the fourth step, we compute u average equals a half u of tk xk plus upred, and for the fifth step we set x of k plus 1 to equal xk plus h times u average. The local error incurred after one Runge-Kutta step is of order h cubed, so after k steps the global error should reasonably be of order k h cubed, which is equal to of order tk h squared. Now let's discuss the trapezium rule. For the first step we compute uk is equal to u of tk. For the second step we compute u temp is equal to a half u of tk plus u of tk plus 1. For the third step we set xk plus 1 to equal xk plus h times u temp. The error incurred at each application of the trapezium rule is of order h cubed. The general trapezium rule is xk plus 1 is equal to xk plus a half h times u of tk xk plus u of tk plus 1 xk plus 1. Note that this is an implicit method as it requires an equation to be solved for xk plus 1. Next, let's discuss the 2D particle path problem. The particle path problem is dx over dt is equal to u and dy over dt is equal to v, with some initial conditions x of 0 is equal to x0 and y of 0 is equal to y0. Then let's discuss the 3D particle path problem. For a 3D flow field with velocity u is equal to u of xyz ti plus v of xyz tj plus w of xyz tk, the particle paths satisfy the system dx over dt is equal to u, dy over dt is equal to v, and dz over dt is equal to w, with some initial conditions x of 0 is equal to x0, y of 0 is equal to y0, and z of 0 is equal to z0. In vector form, a succinct way of expressing these is dx over dt is equal to u with x of 0 equal to x0, where for 3D flow x is equal to i plus yj plus zk. Note that in each case we have more than one equation to solve simultaneously. Now let's state the problem of interpolation. Suppose we only know the velocity u of x at a sequence of n plus 1 points or nodes xk for k going from 1 to n plus 1. That is, we know uk is equal to u of xk for k from 1 to n plus 1. We want to infer the information about u at all points of x given these data values. Next, let's discuss interpolating polynomials. We choose to approximate the velocity field u of x by a polynomial representation over an interval x from a to b. Our goal is to compute a polynomial passing through all nodes, which we can use to approximate the values of u between the nodes. In general, we need an nth degree polynomial to interpolate n plus 1 point. An nth degree polynomial is the general form Pn of x is equal to a1 x to the n plus a2 x to the n minus 1 plus all the way up to anx plus an plus 1, with n plus 1 unknown coefficients a1 to an plus 1. At each node xj, we enforce the condition Pn of xj is equal to u of xj, and use the polynomial to interpolate values for u between the nodes. Hence, let's discuss the direct approach. In a direct approach, we write out the equations at the nodes explicitly, i.e. a1 x1 to the n plus all the way up to an x1 plus an plus 1 is equal to u1, all the way up to a1 n plus 1 to the n plus all the way up to an xn plus 1 plus an plus 1 is equal to un plus 1. But this is a linear system of the form v.a equals u, where the matrix V is given by V equals, on the top row, x1 to the n, x1 to the n minus 1, all the way down to x1, 1, and then at the bottom row, x n plus 1 to the n, x n plus 1 to the n minus 1, all the way down to n plus 1, 1. And the solution vector to be found is A is equal to the vector a1 done all the way to a n plus 1. And the right hand side vector is u equals u1, u2, all the way up to u n plus 1. We call V the van der Mode matrix. Next, let's discuss a useful result for interpolating polynomials. Given n plus 1 points, x1, x2, all the way up to xn plus 1, and n plus 1 values u1 all the way up to un plus 1, there exists a unique polynomial Pn of x that for which Pn of xj equals u of xj holds for j from 1 to n plus 1. Now, let's discuss the drawback of the direct approach. The direct approach suffers from problems with ill conditioning. Suppose we fix the position of the end nodes at x1 equals 0 and xn plus 1 equals 1, and then increase the total number of nodes. When we do this, the spacing between consecutive nodes xi minus xi plus 1 goes down. Since the modulus of the determinant of V is equal to the product from j equals 1 to n of the product for all I greater than j up to n of the modulus of xi minus xj, this means that the modulus of the determinant of V decreases and the matrix becomes singular and the system becomes ill-conditioned. Ill-conditioned systems lead to large round-off errors when a solution is calculated. Also, the system is sensitive to small perturbations. Now, let's move on to discuss Lagrange interpolating polynomial. We introduce the nth degree jth Lagrange polynomial Lj of x, which is constructed so that Lj equals 0 at all nodes xi with I not equal to j, and Lj equals 1 at node xj. So Lj of x is equal to product for all k from 1 to n plus 1 but not including j of x minus xk divided by the product from k equals 1 to n plus 1 but not including j of xj minus xk. Note that the denominator is a constant and the numerator is an nth degree polynomial in x. Lagrange's interpolating polynomial is given by the linear expression Pn of x is equal to the sum from j equals 1 to n plus 1 of u of xj times Lj of x. Note that we showed a polynomial interpolation through a finite set of points is unique. Therefore, the Lagrange interpolating polynomial is the same as that which would have been produced by solving the van der Mode system. For the rest of the video, we will focus on the second half of the spring semester, so we will only consider inviscid, incompressible, irrotational 2D flows. First, let's discuss the definition of complex potential. For a 2D flow which is both incompressible and irrotational, we have seen that the partial derivative of psi with respect to x equals u, which equals the partial derivative of psi with respect to y, and the partial derivative of phi with respect to y is equal to v, which is equal to minus the partial derivative of psi with respect to x. We can recognize these as the Cauchy-Riemann equation, where phi is the real part and psi is the imaginary part of a complex function. The complex potential is defined as w of z is equal to phi plus I psi, where z is equal to x plus iy, and it is an analytic function of the complex variable z. Note that on a solid boundary, psi is constant, hence the imaginary part of w is constant on a solid boundary. Next, let's discuss velocity in terms of complex potential. The derivative of a complex function can be written in terms of its real and imaginary part, as dw over dz is equal to the partial derivative of phi with respect to x plus I times the partial derivative of psi with respect to x, which is equal to u minus iv. The magnitude of velocity at any point is given by the modulus of dw over dz, which is equal to the square root of u squared plus v squared, which is equal to the modulus of u. Then, let's discuss some simple examples for complex potentials. A source of strength K at z is equal to z0 has complex potential W equals K over 2 pi log z minus z0. A sink of strength K at z equals z0 has complex potential W equals minus K over 2 pi log z minus z0. A vortex circulation gamma at z is equal to z0 has complex potential W equals minus I gamma over 2 pi log z minus z0. And a dipole of strength mu in direction alpha at z is equal to z0 has complex potential W is equal to minus mu e to the I alpha z minus z0. Next, let's discuss combining simple examples. As the equation of motion, i.e. Laplace's equation, is linear, we can superimpose solutions. Note, all the flows we will consider are combinations of uniform flows, sources, sinks, vortices, and dipoles. Now, let's discuss the image system for flat walls. If the complex potential without a solid wall along the x-axis is W equals f of z, then the complex potential with a solid wall along the x-axis is W equals f of z plus f of z bar, all barred. This result is known as the Schwarz reflection principle. Next, let's give examples of image systems for a circle. For a flow with complex potential f of z, if an impermeable cylinder of radius a centered at the origin is added, then the new complex potential is given by W equals f of z plus f of a squared over z bar, all barred. We can show that this satisfies the required condition that the circle the modulus of z equals a is a streamline by writing z is equal to a e to the I theta. Next, let's discuss induced velocity. If n vortices are present, the total induced velocity at vortex 1 is because of vortices 2 through to n. If the jth vortex has strength gamma j and is located at z is equal to z equals zj, then the complex potential is given by W equals minus I over 2 pi times the sum from j equals 1 to n of gamma j log z minus zj, and the induced velocity of the jth vortex ujx plus vjy is given by uj minus ivj is equal to minus I over 2 pi times the sum over all j but not capital J of gamma j over z capital J minus zj. Note that since the position of the vortices is a function of time, this can be recast as a system of ODEs. Writing zj is equal to xj plus iyj, we have that dxj over dt is equal to uj and dyj over dt is equal to vj. Hence, dxj over dt minus I dyj over dt is equal to minus I over 2 pi times the sum over all j not equal to the capital J of gamma j over x capital J minus xj plus I times y capital J minus yj for capital J from 1 to n. Taking the real and imaginary parts, this is a system of 2n first order ODEs with 2n dependent variables. Next, let's discuss image systems and induced velocity. Consider a vortex of strength gamma at z is equal to ai and a solid impermeable wall at y equals 0. We can introduce an image vortex of strength minus gamma at z is equal to minus ai, and this ensures that the solid wall is a streamline. So w equals minus I gamma over 2 pi log z minus ai plus I gamma over 2 pi log z plus ai, which is equal to minus I gamma over 2 pi log of z minus ai divided by z plus ai. So u minus iv is equal to dw over dz, which is equal to minus I gamma over 2 pi times 1 over z minus ai minus 1 over z plus ai, which is equal to gamma over 2 pi times 2a over z squared plus a squared. Hence v equals 0, which proves that y equals 0 is a streamline. The induced velocity at vortex 1 is u minus iv, which is equal to gamma over 2 pi a. Now let's discuss conformal mapping. Consider the mapping of a region of the capital Z plane, where capital Z is equal to capital X plus I times capital Y, onto a region of the lowercase z plane by the transformation z is equal to f of capital Z. If f of capital Z is an analytic function of capital Z, then the mapping z is equal to f of capital Z is said to be conformal at all points where the derivative of f at capital Z does not equal 0. An interesting property of conformal mappings is that f conserves the angle of intersection of two curves intersecting at z equals z0, where f dash of capital Z0 does not equal 0. A consequence of this result is that smooth lines in the z-plane which do not pass through a point at which f dash of z equals 0 stay smooth in the lowercase z-plane. However, a curve which passes through z0 where f dash of z0 equals 0 may have a sharp angle at lowercase z0 equals f of capital Z0. Next, let's give the application of conformal mappings to simple fluid flows. If w equals f of z is the complex potential for a flow in the z-plane, velocity uv, then w equals f of capital Z gives the possible flow in the capital Z-plane with velocity capital U capital V. Given a complicated geometry in the capital Z plane, we can find a mapping z is equal to capital F of capital Z, which gives a simpler geometry in the lowercase z plane. We then find the complex potential in the lowercase z plane, w is equal to lowercase f of lowercase z, and hence obtain complex potential in the capital Z plane, where w equals lowercase f of capital Z. The velocity in the capital Z plane is then given by capital U minus I capital V, which is equal to dw over d capital Z, which is equal to df over dz times dz over d capital Z, which is equal to df over dz times d capital F over dz. Now, let's discuss mapping circles. Consider the transformation z is equal to f of capital Z equals capital Z plus a squared over capital Z, where a is a real number. Since f dash of z equals 1 minus a squared over z squared, the mapping is conformal except at capital Z is equal to plus minus a. We now consider the image of the circle radius a, where capital Z is equal to a e to the I theta, so z is equal to a e to the I theta plus e to the minus I theta, which is equal to 2a cos theta. Hence, the circle is mapped to by a straight line y equals 0, and x is between minus 2a and 2a, with the exterior of the circle mapping to the exterior of the line section minus 2a to 2a. Note that the line of minus 2a to 2a in the z-plane is in fact a branch cut, since z is equal to a half z plus or minus the square root of z squared minus 4a squared. Uniform flow past the flat plate parallel to it is given by w is equal to uz, and thus the corresponding flow past the cylinder is w equals u of capital Z plus a squared over capital Z. Now let's move on to the Blasius formula. Consider a body which is uniform at infinity. To calculate the force on the body, first solve for the fluid velocity, second find the pressure on the surface of the body using Bernoulli equations, and third the force on the body is equal to F, which is equal to minus the integral over gamma of Pn dl, where gamma is a curve enclosing the body. However, it is possible to show that the force on the body can be expressed as a complex integral, where if the total force on the body is F equals Fx x plus Fy y, then Fx minus Fy is equal to a half rho I times the integral of dw over dz squared dz. This is known as Blasius formula. Now, let's discuss the use of Blasius formula and the residue theorem. The evaluation of the integral in the Blasius formula can be simplified using the residue theorem. If f of z has poles inside gamma, then the integral over gamma of f dz is equal to 2 pi I times the sum of the residue over z, where the sum is over all poles inside gamma. The calculation of residue for the pole at z is equal to zr forms a series expansion about zr. The residue is the coefficient of z minus zr to the minus 1. Take f of z to be equal to dw over dz squared and gamma to be a curve enclosing the body and no other singularities. Find the residues of f inside gamma to give fx minus I Fy is equal to a half rho times I times the integral of dw over dz squared dz, which is equal to minus pi times rho times the sum of the residues of f, where f is equal to dw over dz squared. Note that we can also include body forces. For example, for a gravitational field, fx minus I times Fy is equal to minus Ib plus a half rho I times the integral over dw over dz squared dz, where B is the buoyancy force. Now, let's give a brief description of the cutter condition. It says, for a body with a sharp trailing edge, the circulation adjusts to eliminate the singularity in velocity at the trailing edge. Next, let's discuss circulation and lift. Circulation around a body leads to a lift force. The force is perpendicular to the far field velocity. And, as ever, thank you for watching.